Welcome everyone, whoever joined this presentation. Thanks for joining our Lunch and Learn presentation today, depending on what time zone are you in. Maybe it's not your lunch time, but I appreciate you joining this. And my name is Gabe. I'm one of the subject matter experts at Mesa Labs Dog Division. I'm cast away in my office in sunny Florida. And at any time during this presentation, please do not hesitate to ask any questions using the conversation window so we can discuss them when we get to the Q&A session at the end of the presentation. So the agenda today includes why torque testing is important, followed by a brief overview of regulations related to torque testing. We will also take a look at operator safety concerns, and CGMPs, which are the good manufacturing processes here or practices in the US, and electronic record keeping, calibration, and finally, we will review some examples of child-resistant closure testing. So why cap torque is important, you might ask. It is important because the closure torque affects or has an impact on the appearance and functionality of the package. For example, tamper evidence. Until they introduced the tamper evidence bans on closed closure or packages with closures, there was an instance that triggered the whole tamper evidence ban design in Chicago in the 1980s. Somebody decided to put some poison in the Tylenol packages, and several people died because of that. So that triggered the whole tamper evident design, the implementation of it on all packages. And you might be very familiar with them because by today, all of the packages include tamper evident designs, either in the form of a tamper evident band or a shrink foil. There's another functionality consideration and how torque may affect the function of the design. When we talk about child-resistant caps, accidental poisoning may happen if a child-resistant cap is not closed properly to the proper torque value. So when kids take the closures in their hands, it's too easy for them to open, even if they don't apply top load on the cap. There's another aspect of this as well, the convenience. It's important for people to be able to open the closure, and if the closure is tightened too much, then elderly people, for example, who may have arthritis in their hands, they could struggle with opening the closure. And even this gentleman on the video, you can see how difficult it is for him to open that cap. And that's just the water bottle. And at last, it's probably the most important factor, the seal integrity. So obviously, if a cap is not closed properly, then air can get to it, or preservative gases could leak from the bottle, and that will affect the appearance and potency or shelf life of the product itself. Now, on the next slide, I wanted to give you a little regulatory overview of regulations here in the US that affect torque testing. One of them is the FDA CGMP requirement for control of drug product containers and closures, and those are included in 21 CFR Part 210 and 211. There are also requirements for tamper evident closures. Those are in 21 CFR 211.132. And as it relates to child-resistant cap testing, there are requirements by the US Consumer Product Safety Commission, and those are described in 16 CFR 1700. There's also 21 CFR Part 11, which is an emerging, or it's becoming more important nowadays. It's a regulation that sets forth the guidelines on using electronic records and electronic signatures. And our torque testers, most torque testers on the field include some kind of data output with which you can import the data in a computer system, and it's just important on the computer system to comply with those regulations. And I will talk about that a little later here. Now, the United States Pharmacopeia Convention also established some requirements for containers and closure testing. These are described in chapter 659, 61, 671, and 1207. I'm not going to go into details of these regulations. Perhaps if there's enough interest, we can create another webinar in the future. There's also important to talk about safety. So with 29 CFR Part 1910 issued by OSHA, there are requirements for most non-construction employers to identify and abate musculoskeletal disorders, including repetitive motion injuries. And as you will see later down in the presentation, that is an issue with manual torque testing. And of course, there's also an additional consideration regarding machine guarding, and those requirements are laid down in 910 subpart O. Those are to prevent injuries from actuators, broken glass projectiles, and hazardous product spills. In 21 CFR Part 820.72, there are regulations or details about how torque testers or any device basically should be calibrated, and how often, the frequency, traceability, and documentation requirements. And finally, I wanted to mention that there's also a transportation regulation in 49 CFR Part 173 and 78. Those apply to hazardous materials. And even in the pharmaceutical field, there are hazardous materials such as blood products, or in disinfectants, bleach, or in pharmaceutical products, there are high IPA, isopropyl alcohol content, or other flammable liquids. So this transportation regulation requires the closing information to be provided to any person who handles the package, transfers to someone else. And after this regulatory overview, I wanted to take a quick look at standards. So standards are, there are several standards that are applicable to torque testing. Those are either controlled or managed by ASTM or ISO, depending on whether we're looking at the US or international territories. In the US, I included a list of standards on this page that you might find useful. These are primarily related to torque retention, measuring torque retention over time, application and removal torque measurement, downward force on child-resistant closures, but there are more unique, primarily applicable to the pharmaceutical field, or the reverse ratchet and shelling, rarely used, but there are standards for them. And there are some other closure testing standards that are not torque related, but it may be interesting for you to know about. Those are standards related to leakage from containers with threaded closures, or the environmental stress crack resistance of threaded plastic closures. Next slide is just a continuation of the standards. These are not necessarily from the pharmaceutical industry, but still may include information that you find beneficial. One of the bigger organizations is ISBT. It's an International Society for Beverage Technologists, and they have many useful standards, and I strongly recommend them to you to look at. And there are foreign standards involving torque testing. Probably the most interesting one is ISO 13127, which includes or describes the mechanical test methods for reclosable child-resistant packaging systems. And of course, there's the US Pharmacopeia test method that includes container permeation testing, and that describes the process of measuring torque, or the process of applying and measuring torque number of times, and then checking for permeation. So before I take a look at CGMP and manual torque testing, I wanted to talk about safety. Safety with the manual torque testing and the issues with safety. So even though it doesn't look like a dangerous equipment or task, manual torque testing is actually a potential reason for repetitive motion involved microtask injuries. And as you can see, those type of injuries are part of the top 10 most costly injury in the United States, accounting for about $1.8 billion. Of course, this is not just manual torque testing, but it's one of those repetitive tasks that is included in that category. And then how repetitive motion injury may occur is it could occur in manual torque testing because of testing large batches of samples, and how, depending on how much torque is required to remove the closure or how much top load the operator has to put on the closure, this could be a real issue. That's a good example there with the testing of the over-torque, the CRC caps. Over-torque caps may be particularly difficult to remove manually, and some CRC designs may require excessive vertical pressure to be applied on the cap. So if the operator has to apply high torque and simultaneously higher pressure, it is certainly demanding on their muscles and joints. And one good example for that, as it comes to torque testing, is USB 671, which is required for container performance testing. This method requires that the operator closes and opens a screw cap, 12 of them, 30 times. And if we are talking about a package design company or a cap manufacturer or even at pharmaceutical companies, when they do this type of test, they are not doing it just for one product. They might be doing it for hundreds of batches, and then over time that could really be demanding. And this is where automated torque testing can really help in applications like this, so operators don't have to manually open the closure, manually apply the top load, but the automated machine will do that for them. And the test can start it by simply pressing two dual actuation start buttons. All the operators have to do is just place the bot on the platform and initiate or start the test. The test is controlled by a servo motor or a motor that applies constant speed and programmable torque ramp to simulate the manual operator opening the closure, increasing the torque. But the manual operator can't control is how fast the torque is being run or how fast the cap is being opened. The automated machine can certainly do that. Also, with the automated machine, we give pressure regulators, and these are adjustable. So the operators can apply, or the machine can apply repeatable bottle clamping pressure and cap gripping pressure. Of course, top load is also repeatable. It's applied mechanically using a spring-loaded top load chuck. And we can also offer centering bases with a built-in feature magnets that support automatic detection. And almost adjustment-free product changeover. So the operators don't have to make any mechanical changes to the platform and column heights, but they just simply replace the tooling, the bottle clamps, the chuck, and the platform. And based on the magnetically coded bases, the machine recognizes the design and it selects the correct recipe. So another safety consideration that comes with, or issue that comes with both manual and automated testing is the spill of hazardous materials, blood products, or corrosive materials, and the breakage of glass bottles and pressurized bottles having some projectiles or creating projectiles. The solution to that on our machine is to guard the system. So if there's any issue, it stays within the enclosed area and it doesn't affect the operator. We also incorporate safety considerations in our machine by implementing dual actuation safety start functionality. And this example on the slide is the two-hand control with anti-bridging, which means actuations cannot be initiated without the use of both hands. So operators have to press both buttons at the same time with their different hands. And then also there's the anti-tie down function. So operators cannot just tape one of the push buttons down, but they actually have to release the buttons and press them again the next time when they want to initiate a new cycle. And there's the anti-repeat functionality, which does not allow them to keep the two fingers and the two push buttons to initiate test cycles, but they have to remove them between the two cycles. And then we can also mitigate safety risks by reducing the pressure of the actuators. There are pneumatic actuators on the machine that limits the pressure applied by these actuators. And we also have remote and built-in e-stop for stopping any cycle if accidents occur. Now, going forward, I wanted to mention CGMPs or CGMP issues. So the current good manufacturing practices by the FDA requires that manufacturers follow certain procedures to ensure that the quality of the product is repeatable and the process is well documented. And these requirements are included in 21 CFR Part 210 and 211. There are some common recalls that I found on the FDA website, and these recalls would be typically avoidable by incorporating torque testing in a quality assurance program. These recalls, just the examples: defective containers, bottles that may not have tamper evident seals properly seated. We could capture or catch that with torque testing, or visual, but we don't do the vision inspection, we just do torque testing here. There's also defective containers, complaints about leaking bottles, defecting child-resistant functionality, ratcheting opens the CR closure where it should stay open, or it's very easy to shell the outer part of the cap design. And then sometimes there's no CR closure for products that should actually require a CR design. This is not so much a torque issue, but it's still interesting to mention. And other times, manufacturers or the FDA during inspections or consumers reported multiple liners in the closure. This could be definitely captured by doing torque testing. There's also the failed stability and discoloration patency tests due to air getting to the products, which clearly indicates that the cap wasn't sealing or the seal wasn't properly on the opening of the bottle. There are also calibration related issues, not having a frequently calibrated machine, or not having calibration sticker on the machine, not having documentation about the calibration, and also the record keeping related issues. So this slide, I guess it's just going through, it's basically a repeat of the other one with some pictures here. And those are actual pictures either from FDA recalls or pictures that I took at customers due to the failed caps. One of them you can see due to over torquing, the yellow cap cracked horizontally. There's another one just below that. Again, it's another one of those caps that fail due to over torquing. Those phenolic caps that are typical on glass containers, those are very rigid and very easy to break them. There's also that some other depth defects on those pictures there. One of them is a vertical crack and the other is just during capping, how the capping equipment damages the outside of the closure. And on the next slides, I kind of want to go through issues with manual testing, and even if you do manual testing, you should pay attention to these issues. Or if you're ready to move to automated testing, these are the reasons why you should, or what is going to be better when you move to automated testing. So one of them is that it's oftentimes difficult to clamp a container without distorting it, or different operators clamp the bottle to different pressures, and a different pressure depending on the bottle design, or in this case it was a jar, it will distort differently. Now, when you try to apply a closure or measure removal torque on a closure, it's distorted like that. It's going to have a different value than if another operator does it properly and the opening is not distorted. Another potential problem is when the operator leans on the bottle and pushes the center of the rotation of the cap out of the center of the measuring platform. That could obviously affect the torque reading as well. Now, it's also important to mention, especially with light weighting of caps, that operators apply varying gripping pressure. So the more pressure they apply to remove the cap, the more friction they may be introducing between the bottle and the cap threads. This could be amplified by not having a slip agent in the cap, in the plastic material. So it's also important to understand the composition of the plastic. With automated torque testing, we can ensure repeatable closure gripping. We either use a serrated chuck, but that's not on the picture below, or the pressure actuated chuck, which is demonstrated on this slide. As you can see, this is a pressure sensitive cap, and at 70 psi gripping pressure, you can see how the cross section is becoming oval and distorted. And at 40 psi, which was optimized for proper gripping, the cross section is not affected, so we would get accurate torque readings. And that's just to point out that sometimes it's not enough that you change to an automated tester, but it's important that you find the right settings for that automated tester. And on the chart on the right side, you will see an example of how chuck gripping pressure was affecting the torque reading. So I applied a number of bottles at various torque or the same torque value, and then I was measuring the removal torque at varying chuck pressures, and then you can see how it's almost like 100% increase of the torque between 20, 40 psi to 80 psi gripping pressure. Now on the automated machine, we have several different gripping options, cap gripping options. These allow repeatable measurement of closure torque, either with temper evident, child resistant, or pump dispenser features. I just wanted to point out that depending on the cap design, you may require a different chuck option. And if you have any questions, please feel free to add them to the message window. So then on the next slide, I wanted to show you that operators, if they don't pay attention, they can easily create a bridge between the cap and the bottle. So at that point, they are not truly measuring, or not measuring the true removal torque, but they're measuring the friction between their hands and the bottle as well. And in that respect, the automated torque testers or the serrated chucks are a much better option. Just be aware of that if you happen to have a narrow or short cap design. 1 second here as I'm trying to start the video. On this video, I wanted to demonstrate one issue with a manual torque tester, or one type of manual torque tester. That is the one with these plastic indicators. Now, because those indicators have their mass, have their own mass, because of that, the display torque value will be highly dependent on how fast the operator is rotating the cap. So in this case, I intentionally was careful and I was rotating the cap slowly, and you can see how the torque was measured accurately. But on the video below, you will be able to see that I was removing the cap with an uncontrolled motion, and you can see that those indicators are pretty much randomly settling on the scale, on the torque reading scale. So the readings are absolutely inaccurate there. The next page, I wanted to show that even if you change to a manual, from manual or a manual analog to a manual digital device, you could be running into a similar issue depending on how fast the data acquisition module is in the digital torque tester. This is an example of me rotating a magnetic torque standard, the top of the magnetic torque standard in a manual device or a manual torque tester. And on the video below, you can see that when I'm rotating it with a low speed, I'm getting fairly consistent readings. But by the second time or third time even, I was rotating it at varying speeds, and then I was getting torque readings from anywhere between 13 inch-pound to 31 inch-pound, which is, you know, it should be the top of the line technology-wise. These should be very accurate as far as the digital technology and the sampling time and everything, but in real life, they are not quite there yet. So that's another, that brings up another important part, is if you keep using manual devices, just make sure you train your operators so they are controlling the rotation of the cap. It's also important to mention that there are process variations that may be causing torque reading variation. These process variations may be something like the liquid product with a high sugar content spilling on the bottle threads and then becoming a thread locker after becoming a solid between the threads. So be aware of that. I've been to customer sites where that was an issue, but more commonly problems are related to not understanding that it's important to control the dwell time. That's the time between the application and the removal measurement. So always tell operators to test the removal torque in a given or in a specified time after the application. Whether it's 5 minutes or 10 minutes, it doesn't really matter. Just make sure they understand that torque needs to be measured always at the same time after the cap was applied. There's also possible process variation due to the aluminum liner not sealing properly or sealing differently on caps that were tightened to a higher torque versus lower torque. And there's also process variation that's included during hot filling processes. And that's just amplified by issues with the dwell time. So, for example, if during the hot fill process, you take the torque measurement immediately after hot filling, then the torque reading will be lower because the plastics are softer. But if you wait 2 hours and the bottle and the cap cools down, then the cap will shrink onto the bottle threads and the torque readings will be considerably higher. Oops, it jumped to another one. Here, I just wanted to show how, or contrast how automated torque testing is better than manual by automating and making the bottle clamping and cap gripping more repeatable. This video also demonstrates the use of a magnetically coded base. So that base is allows the automatic recognition of the bottle and cap. And then just by pressing the 2 push buttons, we initiate a cycle and measure the removal torque at the same time. That's another benefit of the automated tester. We can automate a number of different operations into one cycle. And then the changeover is as easy as removing those bottle clamps and replacing the cap gripper, replacing the bottle base, and just pressing the 2 push buttons again. This is another base that was coated differently with a magnet, and then the screen shows that it automatically changed to the different test profile. The test profiles can be only different either in just the acceptable removal torque range, but in some cases, especially if there's a reapplication cycle, the reapplication torque may be different for a smaller bottle, smaller cap, versus a larger bottle and larger cap. So in the next step, I just wanted to take a quick look at electronic record keeping and how to comply. Basically, what we do is we provide a simple data output from the torque tester to a compliant software package. That software package may be a Torque IQ, which is a rebranded version of WinSPC. There are other software options out there, from Infinity QS to Zontech, and many more. Typically, like in this slide I mentioned, the torque tester, we try not to make the torque tester compliant itself, but we make it as simple as possible to use it just like a weight scale, so it doesn't store data, it just passes data to the system that manages the data. And we offer different communication options for close range RS-232, which is native to the machine, but we also offer USB adapters or for longer distance wired and wireless Ethernet options. And the SPC software that we offer, the Torque IQ, it's not dedicated to torque testing only. You can use it for any other measurement. It can be made compatible with leak testers, CO2 or pressure temperature testers, and connected to several other devices. MESA can customize the machine data output to meet your specific needs. If you're not using any of the software options I mentioned, but you have your own and your software requires a specific data output, we can customize that for you. And in the case of WinSPC, the user accounts can be imported from a Windows domain, and one of the main requirements with 21 CFR Part 11 is that data to be stored and encrypted and password protected in a database. So that's included with the Torque IQ as well. And auditing is enabled or can be enabled for logins, data capture, and configuration changes. Calibration is another important aspect to ensure accuracy, whether it's manual or automated testing. And typically, the FDA recommends, or it's an industry standard that users calibrate their measuring devices annually. Our torque tester basically uses a strain gauge. It's very similar to a weight scale. So if you have a policy for the calibration of the weight scale, then the same would apply to the torque testing device. The regulation governing the calibration of these devices is in 21 CFR Part 820.72. If you want to look at it, they don't really require or tell you how often the testers need to be calibrated. They just want to make sure that you have a documented and repeatable way of calibrating the device, and you calibrate it regularly. So I could even see users calibrating their machines 1, 2, 3 times or every 1, 2, or 3 years. If in the interim they incorporate verification, which I will talk a little bit later. It's important to mention that with the calibration, the process requires a trained calibration technician. And our company in MESA, we have an ISO 17025 accredited calibration lab. So if you require calibration, we can provide it for you. but we can also offer just a calibration kit that you can buy and do the calibration on your own, and we can help you with that process. The kit includes what you can see on the picture is a wire, some dead weights, pulleys, and a calibration frame. And I mentioned verification. So this is probably even more interesting. I mean, it's equally interesting and important than the calibration. But what I really like about verification is that it does not require a trained operator. The operator just, they can just place the gold bottle on the platform of the torque tester and start the test cycle, and the machine will measure the breakaway, the magnetic breakaway torque of that gold bottle displayed on the screen. And if that measurement does not match the set point on the gold bottle that we calibrate in the factory, then you know that something happened to the torque tester, and torque tester should be either recalibrated or serviced because there may be a problem with the strain gauge. So the benefit of this is that it's quick, it's compatible with many testing devices, not just our devices, but manual, automated, and other brand devices. And the accuracy check can be performed with minimal training. The neck adapters can be customized. The set point can be adjusted to different torque levels. And that torque level is determined during a calibration in the factory. But if you send the gold bottle back for recalibration, we can reset it to a different value. The gold bottle can be verified or should be verified and calibrated annually. So talking about child-resistant closure testing, that's very important in the pharmaceutical field. And this is just a good graph to represent, or charts to represent how much poisoning cases were reduced after the introduction of child-resistant closures. So while in the 70s, there were hundreds of cases or deaths due to poisoning, by now those cases are substantially lower. So child-resistant testing is necessary because, and not just in the pharmaceutical field, because medication, household products can include poisonous agents, antidepressants, disinfectants, alcohol cleaning agents, or pesticides, herbicides. And the prevention is to keep, obviously, these poisons out of reach, especially from children, sometimes especially from children. And the way we can do that is to use child-resistant packaging, and child-resistant package testing requirements and package design requirements and testing requirements are described in 16 CFR Part 1700. So when we talk about child-resistant closures, there are just there are a wealth or a number of different designs that are available on the market. Sorry about that. So there are many different designs. Some of them require the operator to press the sides of the closure, and others require a push down and turn functionality. And at the ASTM F250 subcommittee, they maintain a design, a standard, or not a design, a standard classification of all the child-resistant package designs. So you may want to take a look at that. There's a lot you can learn from those existing designs, but it's also important to mention how many different designs are there, because that way you understand why the machine or the test may need to be changed depending on the child-resistant designs. Okay, so I'm trying to go to the next slide. All right. These are standards that are related to the child-resistant closures, and I already think we already talked about this in the beginning, and this is just to show you how we incorporated the top load measurement in our short torque 120 servo machine, so you can measure torque and top load simultaneously. This on the screen you can see on the top part that there's a torque graph, and on the chart below there's the top load. We use strain gauge to measure top load as well, not just for torque. And then for the top load strain gauge, annual calibration is also recommended. And the way we control the top load, it could be either pneumatic or it could be the spring-loaded mechanism in the chuck. So before we finish, I wanted to show you a couple of examples of child-resistant closure testing. One being a machine that we built with a manual clamping assembly. This we built for Georgia Tech, and they used it for designing a senior-friendly child-resistant closure. So the issue was in that case that Pfizer's customers were complaining that the caps were difficult to open. So they used our machine to find the best cap design that would allow these elderly people with arthritis to open the caps easier, but at the same time still maintain the required child resistance. And on this machine, we use the universal manual clamp, and it's manually operated, which means it's slow, but on the other hand, it maximized the number of containers that they could try. And the same thing is true for the adjustable and manually adjusted the 4-post chuck design that they used. On this machine, for the safety, to eliminate safety concerns, we also use the manual platform actuating mechanism. The second example here, I believe this machine we built for the US CPSC, and this was allowing them to measure removal torque on child-resistant closures. The operation is very similar, or the screen design is very similar, but here the operation is completely automated. So it includes digital top load monitoring, pneumatic actuated top load, and we are measuring angle and torque and displaying both the torque and top load on a chart, and the machine is also outputting that data to a computer. On the left side, there is an example of one of our customers using, instead of using a specific or a bottle that can vary, they designed their own neck that was always the same, and then using that neck, they could evaluate their depth design and the variation coming from the different injection mold cavities. And the last example, I just wanted to show you what I already mentioned, that not all child-resistant caps are the same. So this is just an example of 2 different designs with the same diameter, but we received a complaint from the customer that after changing over to the new child-resistant cap, the torque readings were not the same. And then we analyzed the issue and found that the reason for the torque variation was due to ratcheting, and the tester was detecting a ratchet torque and validating as a true removal torque. But in reality, that ratchet torque is not the removal torque. So we had to incorporate some additional tests and validation to make sure that the torque value displayed on the screen is actually the true removal torque. And this kind of test may be important when you do, or programming ability may be important when you do tests that are described in ISO 13127, which requires that the machine or operator presses down the cap, the outer shell of the cap, while simultaneously turning the cap, and then apply progressively increasing top load on the outer shell. And on the screenshots below is actually those are actual screenshots from a test, and you can see on the right side how during the removal cycle, as the top load was increasing, which is represented on the bottom chart, on the top chart you can see the torque, and you can see how during each time the cap was ratcheting, there was a peak, and eventually when there was enough top loads to engage the cap finally opened. So at that point, there's no more peaks at the end of the cycle. And I think we just reached to the end of this slide, and I hope that it was informational, you learned something from it, and I'd like to see if we have any questions from you.
So Gabor, we did get a comment or question here. I can't quite tell, back when you were talking about some of the safety features about these systems being used in beverage factories.
And what was the question?
It just says these systems can be used in the beverage factory.
Oh, absolutely, yes. So automated or manual torque testers are used in beverage factories, and one of, I guess, the safety aspect in a beverage factory is that, especially in the beer industry, is that glass bottles may be pressurized, they may break, and then we protect the operators by using from the projectiles by using those machine guards. But the machines can be used in beverage equally well, can be used in beverage versus pharmaceutical or chemical fields. We have countless of installations at alcoholic beverage facilities like Bacardi or Coke, just carbonated soda, soft drinks, Coke, Dr. Pepper, Pepsi, or juice filling operations, Tropicana, Ocean Spray, other than pharmaceutical companies. Any other questions? I'm trying to bring up the MS Teams window to see if I can take a look at the messages, but it sounds like we don't have any other questions, right, Amy?
Yeah, no, that looks like all of our questions, but of course do get back in touch with us if anybody else has any questions or would like further information from Gabor or anyone at Mesa. Otherwise, I think we are good to say goodbye to everyone for now. So thank you to Gabor for presenting all of his excellent information he knows about the market and our product line, and thanks to everyone on here for attending today.
Thank you.
All right, have a great day, everyone.
Thank you. Bye-bye.